I'm Bill Grob, Director of the National Center for Supercomputing Applications at the University of Illinois and Vice Chair of SC20 Invited Talks. Welcome to the SC20 Invited Talks session on post-von Neumann architectures. The overarching theme of SC20 is more than HPC. Complementing this theme, the Invited Talks collectively focus on applications and technologies impacting all areas of science, engineering, medicine, and society. The distinguished speakers in this session give us a view into the future where post-von Neumann architectures are expected to play a transformational role alongside and complementing mainstream technologies in supporting ever-complex scientific workflows. Catherine Schuman is a research scientist at Oak Ridge National Laboratory, where she works on models and algorithms for neuromorphic computing. She has a joint faculty appointment with the Department of Electrical Engineering and Computer Science at the University of Tennessee, where she co-leads the 10-lab neuromorphic research group.
Hello, my name is Katie Schuman and I'm a research scientist at Oak Ridge National Lab, and today I'm going to be talking to you about the future of AI and HPC, neuromorphic computing, and neural accelerators. So at Oak Ridge National Lab, we currently have the Summit supercomputer, and the Frontier supercomputer is under construction. It will be our first exascale machine. But for computer scientists like me, we're interested in what's going to be coming next after Frontier. How are we going to go beyond exascale? Now, there's a couple of different potential paths forward for this question. I really like this chart from John Schalf and Bob Leland, which shows kind of three axes of different ways we can go. The x-axis shows new architectures and packaging. These are things like superconducting and reconfigurable computing. The y-axis shows new devices and materials, things like spintronics, carbon nanotubes, and graphene, TFETs. Now, the z-axis is what I'm really excited about. This is fundamentally changing the way that we do computation. And this includes different things like adiabatic reversible computing, analog computing, quantum computing, and neuromorphic, which is my research area. So as an AI machine learning researcher, if we're thinking about what our next computer should look like, and we're looking at all of these different potential technologies beyond exascale, beyond the end of Moore's law, beyond the end of Dennard scaling, it would make sense to start thinking about different types of computers that can target AI and machine learning applications. So today I'm going to be talking about two of those, neural hardware and neuromorphic computing. So I'm just going to a little bit touch on neural hardware. I think we're going to hear a talk from Cliff Young later this week. He's going to go into this in a bit more detail, but I really want to provide it as a contrast point to neuromorphic computers. So neural hardware systems accelerate traditional neural network and deep learning computation. They are very well suited to today's existing algorithms. And examples of these sorts of systems are the Google TPU. I'm showing the Google Cloud TPU here. These systems tend to be targeted either towards very fast computation or very low power. So for example, the Google TPU has both a cloud version and an edge version, the edge TPU. These systems exist out in the world today. They're currently deployed in the cloud or in mobile devices, and you can buy them on your favorite online retailer. Now, these accelerate a particular type of computation, traditional neural network and deep learning computation. So what does that computation actually look like? This is probably just a refresher for most of you, but just to give you a reminder, here is a sort of a cartoon level view of a multi-layer perceptron, where we have an input layer, two hidden layers, and an output layer. So what does the computation actually look like here? We have input values coming in the form of a vector, x, and those are going to arrive at our input neurons, sort of stimulating those to fire. To calculate the values at the next layer, we are going to do a matrix vector multiplication where our matrix is made up of the weights of the synapses connecting those two layers. And then we're going to apply a nonlinear activation function, here shown as f, to calculate the vector u. These will be our output values for that next layer. And we're going to repeat a similar style of computation throughout the network. Matrix vector computation, nonlinear activation, and so on, all the way to get our output layer. Now, of course, we can target this sort of computation inside our hardware to get very, very efficient computation. So, in terms of the actual neural hardware performance, here's a highlight for the Google TPU. I'm sure Cliff will talk a little bit more about this later this week. But this is a custom chip that has been deployed in Google data centers since 2015. And it serves billions of people. Probably you've interacted with it this week and haven't even realized it. The first generation TPU ran deep neural network inference 15 to 30 times faster with 30 to 80 times better energy efficiency than contemporary CPUs and GPUs. So by moving this performance into these sort of custom hardware implementations, we can see tremendous performance improvements. So I talk about neural hardware specifically to give a counterpoint to neuromorphic computing, my research area. Because people often lump these two together, but they are actually very different. Neuromorphic computer systems implement a different type of neural network computation, spiking recurrent neural networks, and they can be suitable for neuroscience simulation. They're taking a little bit more inspiration from biology than your neural hardware systems. An example is shown on the slide here as Intel's Loihi system. So there's significant promise in these systems for future algorithmic development. And with these systems, you get fast computation and low power. So Intel's Loihi has an edge version and sort of an HPC version as well, but it's the exact same thing, just the HPC version has more cores in it. Now these systems aren't quite available yet online. They're still in development. They're still very much in the research phase, but they do exist. So what do they actually look like in terms of their structure? A neuromorphic architecture is literally made up of neurons and synapses. In the hardware, those are often physically implemented as neurons and synapses. And there's lots of them. Here I'm showing a sort of grid structure where the neurons are laid out in a grid and then the synapses are connecting them in a grid. But that's not necessarily the case. They can sort of be organized in different ways. But there's lots of neurons and lots of synapses in these neuromorphic architectures. And they operate in a massively parallel way, all of the neurons and synapses potentially operating together. You'll also notice in the neuromorphic architecture sort of cartoon that there's no distinction between computation and memory in these systems. Both neurons and synapses have a notion of computation and memory in the way that they operate. On the right side of the slide, you can see a video which will actually show you the event-driven nature of these systems. Here we're showing the neurons as these sort of spheres and the synapses as the edges connecting them. And then you can see the white spheres operating as the events that are traveling throughout the network. This event-driven nature of neuromorphic computers is part of what makes them extremely low power. So those are just a couple of the characteristics of neuromorphic systems. So I mentioned that although you can't go buy these systems online just quite yet, there are physical large systems out in the world. So here's a couple of the major neuromorphic systems. Two of these, Spinnaker and Brainscales, have been funded by the European Union's Human Brain Project, and thus are very neuroscience driven in the way that they're implemented. They were built to do neuroscience simulations. In contrast, we also have IBM's True North and Intel's Loihi, both developed in industry, that are more computation driven. They're targeted more towards things like machine learning and AI. Now, that doesn't mean that Spinnaker and Brainscales can't do machine learning and AI and that True North and Loihi can't do neuroscience. It just means that the underlying design decisions to build these systems were sort of driven by their different motivations, and that influences the way that they operate and makes it a little bit more difficult to translate programs from system to system because they are very different. Now, these aren't the only neuromorphic systems out in the world. There's also a huge explosion of different types of research chips in terms of different types of devices and materials that are being used to implement neuromorphic. I've highlighted three of my favorites. These three I've actually happened to work with personally, and those include neuromorphic systems that are implemented using metal oxide memristors, neuromorphic systems implemented with superconducting optoelectronics, and there are even neuromorphic systems that are implemented with biomimetic devices. These are devices that are implemented with lipids and polymers that are inspired very much by the way that actual synapses work in the brain. So there's all of these different neuromorphic hardware platforms out there, both in very sort of late stages of development, as you saw in the previous slide, but also in very early stages of development and coming up with new devices and materials to implement these systems. So it's a really exciting time to be involved in the field. And from a computer science perspective, this means that there's a ton of different options in the different hardware backends that we can use. So how does neuromorphic actually compare to neural hardware? There have been some direct comparisons. Neuromorphic systems use less energy on the same deep learning task when compared with neural hardware. In this work, they were comparing Intel's Loihi to Intel's Movidius neural compute stick, a neural hardware system. Also, the Jetson GPU and another NVIDIA GPU and CPU. In this case, the deep learning task was a keyword spotting task where it was using batch size 1. So recognizing a sort of wake word in a particular system, like you might have in a smart home assistant. I won't say any of their names so as to not wake them up in any of your houses, but neuromorphic systems on this task used less energy than a hardware system. Another interesting feature is that neuromorphic had better scalability with larger network sizes. So as the network size increased, the Intel Loihi system's power usage and its inference speed stayed basically the same. Whereas for the Movidius neural compute stick, the power increased and the inference speed decreased. So even on some deep learning tasks, neuromorphic hardware can perform well. But you'll notice here that we aren't implementing the same type of neural network computation. In neuromorphic computing, we're implementing a particular type of neural network computation called spiking recurrent neural networks. These are types of neural networks that take just a little bit more inspiration from the brain and how they operate. So let's delve a little bit more deeply into how these systems actually work. Because it's very important that we understand what a spiking neural network looks like, since it is the way that we are going to program neuromorphic computers in the future. Coming up with the right spiking neural network to solve a problem is the program that we're going to load on our future neuromorphic hardware systems. So spiking neural networks look a little bit different from the traditional artificial neural network cartoon that we saw previously. And keep in mind that this is also a cartoon of a spiking neural network. There's a couple of different features here that make spiking neural networks just a little bit different in how they operate from traditional artificial neural networks. The first key feature is that spiking neural networks have a notion of time in how they operate. Here I list a time component on the synapses. That means the synapses can have a delay where it takes time for information to travel from one side of the synapse to the other. Neurons can also have a notion of delay and a notion of time in the way that they operate as well. You'll also notice here that we get a little bit more complex structures. It's not necessarily organized in that layers as we saw in the traditional artificial neural network. We can have things like cycles or multi-edges, and these make sense in these networks. And in fact, for spiking recurrent neural networks, you can have any two neurons connected to each other by synapse or even multiple synapses. Spiking neural networks also receive input over time in the form of spikes, and they produce output in the form of spikes over time. And you can encode numerical information as spikes by putting more spikes in for larger values, or encoding them with the rate of spikes as they arrive, or even encoding them with the time at which the spikes arrive. So let's walk through a quick animation of this cartoon level spiking neural network doing some processing so you can get a feel for how it actually works. So here we can see some spikes coming into the network over time. And as they come into the network, they will stimulate the input neurons that they arrive at, causing those to generate internal spikes that are also going to travel throughout the network. So as these internal spikes are traveling throughout the network, they're arriving at different hidden neurons in the network at different times, and the timing of those arrivals has an effect on the computation that these spiking neural networks are doing. And so you can see the spikes traveling throughout the network, more spikes arriving at the input neurons, generating more and more spikes throughout, and eventually reaching the output neuron and generating spikes there as well. And so we convert data into spikes that are going to be fed into the network, and then we look at the spikes that are coming off the network to give us an idea of what the spiking neural network is actually doing, and typically give us an answer for some task. So again, this was the cartoon level view of a spiking neural network that honestly took me way too long to make in PowerPoint, but hopefully that helped you understand spiking neural networks just a little bit better. Now here is a video of a real-world spiking neural network that actually solves a real task. What you can see in this video is yellow neurons, which are our input neurons, red neurons, which are the output neurons, and then the hidden neurons are shown in teal. You can see two different types of synapses, both blue and orange, excitatory and inhibitory. Excitatory synapses are positive weighted, which means that they cause an increase in charge on their postsynaptic neuron, making it more likely to fire. Inhibitory neurons are negative weighted, which means that they cause a decrease in charge on their postsynaptic neuron, making them less likely to fire. You can see the flurry of activity of different spikes happening in this network, causing the output neurons to spike and generate more and more spikes traveling throughout. So again, the timing of the spikes throughout this network makes an effect on how the network is actually performing computation and is integral to the way that spiking neural networks process computation. Okay, so how do we actually program using spiking neural networks? So as you may suspect with a neural network, we often use a machine learning algorithm to come up with the right network to solve our problems. So if we're doing like a classification or anomaly detection or prediction task, we may feed in data to our algorithm to produce the network. If we're doing a control task, we may have a simulation environment that we're going to use to come up with the right network to solve our task. So as you may suspect, training a spiking neural network using a machine learning algorithm is a little bit different from training a traditional artificial neural network. But we still sometimes use back-propagation-like approaches to train these networks, just like we would in our traditional artificial neural network sense. But these back-propagation-like algorithms have to be adapted in order to work with spiking neural networks. And one of the first big things that has to be adapted is we have to deal with the non-differentiability of the spiking neurons. It's done in a bunch of different ways in the literature, but something has to be done to combat that in order to use back-propagation-like approaches. You'll also notice that this is organized in a layered structure. Often when we're using a back-propagation-like approach to train a spiking neural network, we're using a more restricted structure in our networks. For neuromorphic hardware, when we're actually mapping the spiking neural network onto it, we often also have to deal with low precision weights. And these back-propagation-like approaches for spiking neural networks use a non-standard approach to dealing with delays in the network. Sometimes they ignore them altogether, sometimes they attempt to train them, but there's basically a non-standard approach into how they actually deal with them. So the key advantage of using back-propagation-like approaches for spiking neural networks is that we have decades of knowledge about traditional artificial neural networks on which to build for this. The key disadvantage is that they don't work natively on many of the features of spiking neural networks, so we're not necessarily taking advantage of all of the potential computation advantages of spiking neural networks when we're using these as our primary training approach. Another algorithm that is extremely commonly implemented in neuromorphic hardware is synaptic plasticity, and in particular, spike timing dependent plasticity, or STDP. In STDP, the timing of spikes throughout the network has an influence on how the weight values of the synapses change. It's basically like a more advanced version of Hebbian learning, in which, sort of neurons that fire together wire together. If the presynaptic neuron and postsynaptic neuron fire in close proximity, then that's going to cause a change in the weight value on the synapse. And the timing of those spikes affects how much the weight changes and whether that changes in a positive direction or a negative direction. So the key advantage for synaptic plasticity mechanisms and spike timing dependent plasticity in particular is that it is a biologically inspired approach to training spiking neural networks. This is something that we have observed in neuroscience and are now implementing in these systems. And it has been shown to have some success on some unsupervised learning tasks. However, the key disadvantage is that it's not well understood, and it hasn't been shown to perform well on more complex tasks. So it's clear that although it can be useful, we definitely need other training approaches as well. So this is where my research comes in. I've been developing an approach called Evolutionary Optimization for Neuromorphic Systems, or EONS, to train spiking neural networks for particular applications and for neuromorphic hardware. And so how does this work? For a particular neuromorphic hardware system and for a particular application that we want to solve, we're going to start with a population of potential spiking neural network solutions. Here I'm only showing 4 potential network solutions as our random initialization there. Our population sizes typically have hundreds to thousands of networks in them. Then we're going to take each of these randomly initialized spiking neural networks and we're going to evaluate and rank them. And so what that evaluation entails is taking the spiking neural network, loading it onto the neuromorphic hardware system, or more commonly a simulation of the neuromorphic hardware system, and then just running it on the application. So testing it on a classification task, for example, and getting a score for how well it's performing. And we're going to do this for every network in our population so that they all have a score and we can rank them from best to worst. Now at the beginning, when they're randomly initialized, they're not all going to be very good. In fact, they're mostly going to be pretty bad, but some are going to be less bad than others, allowing us to establish this ranking. From there on out, we're going to use selection algorithms from the genetic algorithm literature to preferentially select better performing spiking neural networks to serve as our parent networks. We're then going to do reproduction operations like crossover, mutation, and duplication to produce children networks for our child population from the parents. From there on out, we're going to repeat the evaluation and ranking, selection, and reproduction processes with our child population, and we're going to iterate until we get a certain number of generations or we reach a desired performance level. So if you know anything about genetic algorithms, your first question would be, can't this take a long time? There's a reason that it's called EONS. It can take a little bit of time, but maybe it's not quite as bad as you might think. There are a lot of advantages actually using evolutionary optimization to come up with spiking neural networks to solve these tasks. And especially when we don't quite understand what the right training approaches are, it's really convenient to use in the short term. So here are some of the advantages of using evolutionary optimization. The first is that it's applicable out of the box on a wide variety of different tasks. It can work on classification, control, or anomaly detection or prediction without having to change the algorithm. You just have to be able to have a way to score networks and say one network is better than another one. It also works on a bunch of different architectures and devices, again, without changing the algorithm. And as you saw earlier in the presentation, we have so many different neuromorphic hardware implementations, and they all look radically different, and they behave very differently depending on the devices and materials that are used to implement them. So it's important to be able to have an algorithm that can translate across these different systems. It will also operate within the characteristics and constraints of the particular architecture or device that we're using, which is important because some of these neuromorphic hardware systems are pretty quirky. It can also learn the topology and the parameters of the network. We don't have to know what the network should look like ahead of time, although if we do, we can start there. But it can figure out how many neurons you need, how many synapses you need, as well as all of the parameters associated with the network. It can interact directly with the hardware, or it can interact with software simulations. If you do happen to have hardware, it can work with hardware in the loop, and that is something that we've done previously. And finally, of course, at Oak Ridge National Lab and here at Supercomputing, it's very important to note that EONS is also parallelizable or scalable in HPC. I have run it on Summit and also on our previous supercomputer Titan, and I'm very much looking forward to running it on Frontier and also running it on future supercomputers that might have neuromorphic systems in them. It's important to note that you don't have to use machine learning to come up with the right spiking neural network to solve a problem. In some cases, programmers are actually hand tooling these spiking neural networks to solve a particular task. And I'll talk about a couple of those in a little bit. All right, so how do neuromorphic computing and HPC go together? How are neuromorphic computers actually going to be used in future HPC systems? So I wanted to highlight a couple of neuromorphic use cases, and the first one is one that you've probably already thought of, in situ data analysis. So using a neuromorphic processor to analyze data as it's being produced perhaps by a modeling and simulation application. And maybe that neuromorphic processor is producing actions to feed back into the modeling and simulation process, or maybe it's just producing real-time analysis that's being stored or sent to the users so that they can monitor what's going on in the simulation. So that's a very common one, and also probably going to be very popular with neural hardware systems as well. But the two others that I want to highlight are training for deployment and as non-neural network coprocessors. For training for deployment, we could use a future supercomputer with neuromorphic systems in it to train spiking neural networks that could then be deployed out into systems like smart scientific instruments, robotics, and autonomous vehicles. We can also use neuromorphic systems as coprocessors where they're doing non-neural network computation. So I'm going to give you a couple of examples of the latter and what we've done today. But right now what we're doing is simulating neuromorphic hardware on high-performance computers rather than having the physical hardware system right there for us. So we're going to start with training for deployment. So the first application that I want to highlight is a scientific data analysis application. And this was looking at data from the MINERVA experiment at Fermi National Accelerator Lab. This experiment was a neutrino scattering experiment where the MINERVA detector was exposed to a neutrino beam. So we worked with millions of simulated neutrino nucleus scattering events. And the classification task was to classify the horizontal region along the detector where a neutrino nucleus scattering event originated. So This detector produces lots of different kinds of data, but one type of data that it produces is the times at which certain events are occurring. Now, times for spiking neural networks and neuromorphic systems are very well suited to be fed in as spikes at those times when the events occur. So the data maps very naturally to a spiking neural network and neuromorphic setting. So we actually looked at both convolutional neural networks and spiking neural networks as applied to this problem, and we got very comparable results. The difference in accuracy here is negligible. But the interesting thing that we found with the spiking neural network result is that the network to solve this task to get the same accuracy as the convolutional neural network was actually very small. You can see the convolutional neural network structure across the top of the slide, and you can see a couple of fully connected layers at the end there. That first fully connected layer, FC1, has 196 neurons in it. Just that layer is bigger than the entire spiking neural network that was used to solve this task, that had 90 neurons and 86 synapses in it. We also estimated the energy for a single classification on a memristive neuromorphic system to be 1.66 microjoules per classification. So we actually trained the spiking neural network on Titan at Oak Ridge National Lab, and this sort of spiking neural network could then be deployed to a neuromorphic system sitting at the scientific detector to analyze data as it's collected in real time. So another task that we've looked at is autonomous robot navigation, and this was actually a task that was done by 2 undergraduate students at the University of Tennessee, Parker Mitchell and Grant Brewer. So they wanted to build this robot that would navigate and explore an unfamiliar environment while avoiding obstacles. So basically they wanted to be able to take the robot, drop it into a room that it had never been in before, have the robot cover as much ground as possible and not run into things along the way. So basically do a surveillance task or be a smart Roomba. So they wanted to add a couple of challenges into this computation. This was going to be a robot entirely controlled by an onboard neuromorphic system that was going to be given no explicit instructions on how to operate prior to training. What the neuromorphic system was going to receive as input was the LiDAR sensor on the front of the robot, which was sweeping on a servo, giving it 5 readings. Those LiDAR sensor information was going to be fed directly into the neuromorphic hardware system to produce the motor controls of the robot. Left motor forward, left motor back, right motor forward, right motor back. So at the beginning, the robot doesn't even know how to turn left and right. It has to learn how to do that over the course of training. We were going to give it no prior knowledge about the environment, so it wasn't going to know how many obstacles there was going to be or how big the room is. And we're going to train only in simulation. So here's a video of the simulation. I like to joke that the student who made this simulated environment, Grant Brewer, who's now a PhD student at Georgia Tech, you can tell that Grant was a double major in computer science and physics because in all of Grant's simulations, everything's a sphere. The robot's a sphere, all of the obstacles are spheres. So in all of our simulated environments that the robot was trained in, they looked a little bit like this. And as you can see in the video, this was after the network was trained. The robot is navigating the environment and covering as much ground as possible. So even from this very simplistic environment, the network was then deployed onto the physical robot, and you can see the physical robot very adorably, if I might add, navigating its environment and avoiding obstacles along the way. And of course, these obstacles were whatever we could pull out of offices at the University of Tennessee. So in this case, again, we trained in simulation, both simulating the neuromorphic hardware and simulating the environment on the supercomputer, and then deployed that into the physical environment where it was able to operate successfully. A third application that I want to highlight is one that's actually happened in the last couple of months. We at Oak Ridge have been working with researchers at the National Transportation Research Center, also part of Oak Ridge National Lab, to look at using neuromorphic computers to do engine control for fuel efficiency. So we wanted to be able to take a spiking neural network that we trained, deploy it to an FPGA-based neuromorphic hardware system to be able to do the controlling of the fuel injection in an internal combustion engine. So we have actually trained a spiking neural network on Summit using a simulation of the engine, deployed it to a physical FPGA-based neuromorphic hardware system, also developed at Oak Ridge National Lab called MicroCaspian, actually developed by Parker Mitchell, who also built that robot you saw previously. And we have actually operated with it in the loop at the National Transportation Research Center. You can see the board initially here connected to a microcontroller and a computer that are then connected to the engine in the lab. And in this case, the neuromorphic system where the spiking neural network was trained on Summit is actually controlling the engine's fuel injection in real time, getting cycle-to-cycle information from the engine and making those decisions to push back to it. We're very excited about this project, and we're seeing some really interesting results. So those are my training for deployment examples that we have already done, where we're doing neuromorphic simulation on HPC, but those would easily work if we also had neuromorphic hardware on the supercomputer to actually do that evaluation in real time. But there's also this other class of using a neuromorphic system on a high-performance computer as a non-neural network coprocessor. So what are some examples of this that we've been looking at? So about 6 months ago, for no particular reason, a researcher at Oak Ridge National Lab named Kathleen Hamilton realized that we could use neuromorphic systems and models of spiking neurons to model epidemic spread. And in this case, we're basically treating the neuromorphic computer as just any other sort of computer with particular characteristics. What Kathleen realized is that we could model neurons as individuals in a population, synapses as shared social connections, and spikes in the network as transmission of infection. And by setting up parameters in the network, the different weights on the synapses, thresholds on the neurons, delays, and so on, we could set up different conditions, and we could do modeling of epidemic spread. We could do SIR models, and you can see actually here one of the SIR modeling results from a spiking neural network and neuromorphic simulation that we have done previously. You can also do things like graph algorithms using neuromorphic systems. And one of the most popular ones in the literature right now is using a neuromorphic computer to calculate shortest paths. And in this case, sort of the conversion into a spiking neural network is very natural, because you take a graph, you turn every node into a neuron, you turn every edge into a synapse, and then you do some sort of computation on that. So if you have a weighted graph, you can take the distances on the edges and convert them onto delays on the synapses. And then you can have spikes travel throughout the network in order to give you single source shortest paths. If you happen to have a learning mechanism like SCDP on your neuromorphic hardware, you can also get the paths themselves and not just the path lengths. So neuromorphic systems can actually be used as computers and not just neural network simulators. So to summarize, the future of AI and computing in general is likely to include custom hardware like neural hardware and neuromorphic computing. And there are many potential use cases of neuromorphic computing and neural hardware as coprocessors in future HPC systems. I've highlighted just a couple of them in the last few minutes. However, neuromorphic computing systems are non-trivial to program, but there's a lot of exciting opportunity to develop both new machine learning and AI algorithms to build spiking neural networks to solve problems, but also to just figure out how to build a spiking neural network to solve different types of problems, like the modeling of epidemic spread or the shortest path calculation. Now is the time to get involved in the development of these systems. The hardware is still being built. There is a very tight co-design loop that's happening between researchers like me, who are building algorithms and applications, and researchers who are developing the hardware. We can have an influence on what that hardware is going to look like moving forward, and that's really exciting. So if you're interested in learning more about neuromorphic, I'd encourage you to check out a survey paper that I co-authored a few years ago. It's available in arXiv that gives you a lot of information about the field and from a variety of different perspectives: hardware, algorithms, applications, and so on. With that, I'd like to thank my colleagues at Oak Ridge National Lab who've collaborated with me on this work, as well as the 10-lab neuromorphic research group at the University of Tennessee, who've also collaborated with me on this work. This work is supported by the Department of Energy and the Air Force Research Lab. And with that, I thank you very much for your attention, and I'm happy to take any questions you might have. My contact information is on the slide. Thank you very much.